All right, so we're up to 3.6. So I'm going to do 3.6 now. On the schedule, I have until tomorrow to do 3.6. So I was going to do some of 3.6, and then, as I said yesterday, I was going to let you ask some questions. But if you don't ask questions, I'll just keep going with 3.6. Okay? But no matter what, tomorrow, about halfway through the class, or a little bit more, a little bit less, I'll stop and give you the quiz. And the usual routes for the quiz. You know the way the quiz is right now. Okay, so let me start lecturing 3.6. At some point, I'll stop and see if you have questions about any of this stuff. Okay, and if you don't, then I'll just keep going. Okay, so we are up to here, it looks like 3.6. We're about halfway through this longest chapter that we've got. Okay, so that's how far we are. Okay, so we're taking derivative of log functions now on page 218. So the derivative of natural log of x is 1 over x. Okay. Again, if we were meeting face-to-face, I'd make you guys memorize it. Since I'm not making you memorize it, put it on your cheat sheet if you want. Okay. So what about logs to any other base? Then you do this. The derivative of log base b of x, it's still got 1 over x, so that's the same 1 over x, but you have to multiply by ln b in the denominator on the bottom. So clearly it's not so nice. So what's the derivative of log base 7 of x? 1 over x ln 7. Okay. And there's the chain rule also, and I'll show you how the chain rule works. If you want to differentiate ln of u, you go 1 over u, and then times du dx, the derivative of this inside function. Okay, so now let's get started with doing some of those. Okay, so 3.6, please. Page 223. Oh, and yeah, I don't remember if I showed you the problems, but I'll go ahead and do it again anyway. So for those of you that don't plan to get the book, so here's the homework problems on 3.6, 39-ish. Okay. And there's nothing on the next page. All right, now number 3, f of x equals sine of natural log of x. So the outside function is the sine function. Okay? So you differentiate the sine function with respect to the inside. So that's cosine of ln x. And then by the chain rule, it's times the derivative of the inside function, which we now know to be 1 over x. And then the best final answer is to write it like this, cosine of ln x all over x. Okay, number 5, f of x equals natural log of 1 over x. Okay, there's a hard way and an easy way to do this. I'm going to do the easy way. The hard way is to take it literally as it is. To do the derivative of ln, you would go 1 over all that. Right? So you go 1 over x, and then by the chain rule times the derivative of the inside, which could involve a quotient root. Okay, so you'll get the right answer, but there's something much, much easier to do for this. You might recall for ln 1 over x, you can think of it as ln x to the negative 1. Right? And then a property of logs, not taking a derivative, this is even from pre-calc, okay, you can bring that negative 1 out in front and make it look like negative ln x. That makes the problem way easier. Okay, so one more time, write this as ln x to the negative 1, and then the negative 1 gets to come down in front, not because of calculus, that was from algebra. So even in your pre-calculus days, you should already know how to do this. So I'm just differentiating negative ln x, which is just negative 1 over x. The constant multiplying root, the coefficient is negative 1, so the derivative is negative 1 times the derivative of ln x, which is 1 over x. Okay. Now 13, you kind of have that same theme. And let me show you what they have for 13. G of y is ln of a great big mess. So the hard way is to say, okay, I got ln. So you would go 1 over that, 1 over a fraction, and then times the derivative of the inside, which is going to be a quotient root. Okay? That is the super hard way to do it. Okay? Much, much better is to start off by using your property of logs. Okay, so this is g of y is ln of 2y plus 1 raised to the 5th power over radical y squared plus 1. You're taking the ln of the whole thing. Okay, sorry, maybe I'm doing ln of this. All right, so before I differentiate, I do properties of logs. Okay, first I have an ln of a quotient, ln of something divided by something. So it's the ln of the numerator minus natural log of the denominator, which I'm going to choose to write as y squared plus 1 to the 1/2 power. That's what square root means, right? And now I have a property of logs that says the 5 can come down in front and the half can come down in front. Okay, I'm not differentiating yet. This is algebraically equal to this and equal to this. Okay, so one more time, ln of a quotient, something divided by something, ln of the top minus ln of the bottom. Square root means that. And another property of logs says I can bring the 5 in front and the half in front. Now I much rather differentiate this. It's way easier. This thing. So now g prime of y is 5 times 1 over 2y plus 1, and then by the chain root times the derivative of 2y plus 1, which is 2. And likewise, minus a half times the derivative of ln y squared plus 1, 1 over y squared plus 1, and again by the chain root times the derivative of the inside, which is 2y. And very conveniently, I notice that 2 cancels that 2. Okay, so this is going to be 5 times 1 times 2, 10 over 2y plus 1, minus, let's see, the 2's cancel out, so you just have a y over y squared plus 1. And that'll be my answer for that one. Okay, 17. T of z is 2 to the z log base 2 of z. Okay, and just so you know, I will always write my z's with that little mark like that to distinguish it from a 2. So that's my 2. If I didn't put that mark there, you might think, is that a z or is it a 2, right? And frankly, I'm too lazy to, you know, when you write the z, you're supposed to kind of have sharp corners. But, you know, I'm too lazy to do that. Maybe some of you are too lazy to make sharp corners for the z. So my z's are going to have that little mark there. So no mark there, that means it's a 2, not a z. Anyway. All right, so this looks like a product rule. Unfortunately, I've got base 2 here and base 2 here, which means I have to multiply by ln2 in some places. Okay, first function, second function, like fg. So product rule is f g prime plus g f prime. Okay, so first function, copy it, times the derivative of the second. So how do I differentiate log base 2 of z? 1 over z ln 2. Plus second function, log base 2 of z, times the derivative of the first. So what's the derivative of 2 to the z? 2 to the z ln 2. Okay, that's essentially it. All I did here was slide that with the 1. So 2 to the z over z ln 2. And then all this, I just kind of rewrite it better. So 2 to the z log base 2 of z times the natural log of 2. Okay, so there we go. So you can see if we don't have base e, it's harder. Looks like you have base 2. So to differentiate 2 to the z, 2 to the z ln 2. To differentiate log base 2 of z, it's 1 over z ln 2, right? Show you that again in the text. Page 218. Derivative of log base b of x, 1 over x ln b. If you have natural log base e, it's simple, just 1 over x. So it's only when you have a base other than base e, like base 2 or 3 or 10 or 20, that you have to play this game here. Okay. All right, I'm going to take a little bit of a timeout and show you some stuff. Okay, so we said the derivative with respect to x of natural log of x is 1 over x. Okay, we already know that. What's the derivative with respect to x of ln negative x? Okay, so that looks like a chain rule. So it's ln of something. So first you go 1 over that. So 1 over negative x. And then by the chain rule, it's times the derivative of the inside function, which is negative 1. Okay, so I have negative 1 over negative x, which is still 1 over x. Okay, so in short, what am I trying to say right here? The derivative of natural log of x, 1 over x. Derivative of ln negative x is also 1 over x. Okay, so what does that all mean? The derivative with respect to x of ln absolute value of x is 1 over x. Okay, so if you have ln absolute value of x, the derivative is 1 over x. Now, frankly, you don't have to do that many problems right now involving absolute value. I mean, they got it over here. Okay, but in our last section of Calc 1, our last chapter, chapter 5, we're going to come back to this theme. Okay, so just kind of put this on code storage, but maybe toward the end of our course, probably late November, early December, I will come back and say, remember a long time ago we saw the derivative of ln absolute value of x is 1 over x. Okay, I'm going to bring that back. That will get resurrected back then. So probably around Thanksgiving time, maybe late November, early December, I'll bring this back up. That's not until chapter 5 near the end. Okay, now why does this work? Okay, well, absolute value of x is either x, if x is greater than or equal to 0, or it's negative x, if x is a negative number, right? So absolute value of x, it might be x, in which case the derivative is 1 over x. It might be negative x. If the absolute value of x is negative x, then I'm doing this. But we've already seen, even in this case, I still get 1 over x. Okay? So in either case, whether I have x or negative x, the derivative comes out to be 1 over x, which now allows me to say the derivative of ln absolute value of x with respect to x is now 1 over x. Okay? If you want to put that in your cheat sheet, you may. Most of the homework problems right now, you're going to differentiate just ln x. Okay, but if they sneak in an absolute value, you still do the same thing. Okay, and once again, we're not going to see that absolute value too much until chapter 5, where it'll come back. Okay, and let me show you in the text. Yeah, here we are. On page 220, the derivative with respect to x of ln absolute value of x is 1 over x. Okay, so we have ln absolute x, same thing, still 1 over x. All right, so I'll show you something like that. Okay, 25. Y equals natural log absolute value of secant x. So don't get thrown off by that absolute value. You just do the same thing as if it said parentheses. All right, so you just go 1 over this, 1 over secant x, and then by the chain rule, it's times the derivative of secant x, which is secant x tangent x. Well, very conveniently, the secant x cancels out, so I just have tangent x. So y prime is tangent x. It asks for y double prime, so that's easy. Y double prime is just the derivative of tangent x, which is, again, secant squared x. So the answer is just secant squared x. Okay, then 33. This theme again. Find the equation of the tangent line to the curve at the given point. So the book doesn't let you forget this. Yeah, very long. Okay, so same thing. This has a graph. Okay, you're at a certain point. What's the equation of the tangent line? Whatever this looks like. Okay, it might have some weird looking shape. Okay, but at that certain point, there's going to be a tangent to the curve. We want to come up with the equation of that tangent line to the curve. Okay. All right, so y equals natural log of x squared minus 3x plus 1. The point is 3, 0. So you have a point, you need the slope. How do I find slope? Derivative. So derivative gives me the slope, and then I plug in. So what's the derivative of ln of whatever? Well, 1 over whatever times the derivative of whatever. So what's the derivative of x squared minus 3x plus 1? 2x minus 3. And then, of course, you just slide the 2x minus 3 over with the 1. 1 times that is just 2x minus 3. So here's my dy dx. Here's my derivative. 2x minus 3 over x squared minus 3x plus 1. Now, I have a rule. I have a rule for the slope at any x. So you give me any x, I plug in. What is the x to give me? 3. So I plug in 3 right there, and right there. So I have 2 times 3 minus 3 over 3 squared minus 3 times 3 plus 1. Okay, so that gives me what? 6 minus 3 is 3 on top. And the bottom is 9 minus 9. Oh, that's 0. Plus 1. So 3 divided by 1, 3. Right, so the slope of the tangent line at that particular given point, 3, 0, whatever this graph looks like, the slope right at that one point is 3. Okay. Point, slope. Point slope form. Y minus y1 equals m times x minus x1. There we go. And we're done. Okay, that's as much as I was willing to do, but I'm willing to do, or that I needed to do, put it that way, but I'm willing to do more. Okay, so I'll be done in a few minutes. Okay, so if you want to start thinking of questions you want to ask me or put it in the chat or ask Prasanna, that's fine. But if not, I'll just keep going. So even right now, as I'm blabbing another few minutes, if you want to type a question in the chat for me to do from chapter 3, I'll let you do that. Okay, but I'm introducing something called logarithmic differentiation now. What is this weird logarithmic differentiation? So that covers the problems at the end, which was 39 to 51. Okay, so 3 to 33 are just quote-unquote regular problems involving logs. 39 to 51 is this weird logarithmic differentiation stuff. Okay, so what is the concept of logarithmic differentiation? Okay, so 39 to 51, use logarithmic differentiation to find the derivative. Okay, so before I touch any of these, let me go back to something like 13, right? We did 13, right? Now, if I didn't have that ln, if that ln weren't there, it'd be a pretty messy derivative, right? You would have a quotient rule, bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the square of the bottom, right? But because there was an ln there, it made the problem much easier, made it much nicer. Okay. I also see some problems we haven't tackled yet, where it looks like you have a variable expression to another variable expression, variable to a variable, like x to the x, or x to the sine x, or tan x raised to the 1 over x, or something like that. Okay. They have to be done by something called logarithmic differentiation. Okay. So I'm just introducing the concept right now, but the game we're playing is this. Okay. I've sort of given away the game already by putting it. Okay. 41, y equals square root of, what is it, x minus 1 over x to the 4th plus 1. Okay. If you were to take it like that, it's very, very messy. You could. Okay. You would have to go blah, blah, blah raised to the 1/2 power, right? X minus 1 over x to the 4th plus 1 raised to the 1/2. So it would start off with 1/2, blah, 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 to the negative 1/2. And then by the chain rule, times the derivative of the inside, but that's going to be a quotient rule. Okay, it's very, very messy. So the game we're playing is this. We're saying it would sure be nice if there was an ln in front of the whole thing. So that's what we do. We put an ln, but you have to put the ln on both sides. Like this, ln, ln. See, once there's an ln here, you can get the ball rolling, and you can use the same properties as you did for 13. Okay. The main difference is that the left-hand side isn't just y, it's ln y. Okay. So ln y equals ln of all this. But once you have this, now you can start playing the game of putting the 1/2 in front and doing ln of a quotient, which becomes much nicer. Okay. Difference being that the left-hand side isn't y, it's ln y, okay, which means you'll have to do implicit differentiation after that. Okay. So I was going to show you that tomorrow. But the main idea here is we say to ourselves, wouldn't it be nice if there was an ln? Then I can use my log properties, just like number 13. So we say, okay, I'll just put in an ln. Once I put the ln, I can do stuff like bring the half in front, take ln of a quotient as that, and now this derivative becomes much, much nicer. Okay. So from this stage, you're going to implicitly differentiate. Okay. So what's the derivative of the left-hand side? Because there's an ln y, you would go 1 over y times dy dx, right? And then you would differentiate this side. All right, so there's something else I'm going to show you before I stop very quickly. Show you the different things that we have to watch out for situations where you have a variable involved. Okay, y equals x squared. Okay, that's a variable raised to a constant. That says constant, C-O-N-S-T for constant. There you're doing a power root, so y prime is 2x. If it's reversed, if you have y equals 2 to the x, a constant raised to a variable, that's the exponential function. So y prime is 2 to the x ln 2. So in other words, when it looks like this, do not go x 2 to the x minus 1. Don't do that. Okay, that's only for this situation. That's the power root. Variable, like x, raised to a constant 2. This is a constant raised to a variable. That's an exponential function. And then for something like 43, you have a variable raised to a variable. You're going to do this logarithmic differentiation. Okay? And you might say there's one case I left out that was a constant to a constant. Well, yeah, if you have a constant to a constant, it's still a constant, right? Like 2 to the 50th power. What's the derivative of 2 to the 50th power? 0, right? It's still a constant. Okay, so please note this. Variable to a constant, like x squared, power root, 2x. Constant to a variable, like 2 to the x, exponential function root, derivative is 2 to the x ln 2. Variable raised to a variable, like x to the x, logarithmic differentiation. So that means I will take the natural log of both sides first, right? I'll show you more of this tomorrow. ln y equals ln x to the x. See, I don't like that x to the x. See, how can I get that x down? By putting an ln here. Then once I have the ln, the x gets to come in front. So it'll be x ln x. Okay, so I'll stop there and I'll take questions if you have any, but if you don't, I'll complete this and this. But if not, I'll show you this tomorrow. Okay, so let me put this away. Unfortunately, I can't see the chat and share the screen at the same time. So let me stop the share and check the chat. Okay, so I see 3.59 and 3.449. Okay, so let me get my board here. Let me just put down in my scratch paper 3.5, number 9, 3.4, 49. Okay, and if anybody has some others, put it now, because I can't see them at the same time. You can still put it, but I'll come back to it later. Okay. Anybody, or you can just unmute yourself. So I'll give you another 10 seconds. Anybody want to put in the chat a question that you want to look at, or unmute yourselves? Otherwise, I'll just do these problems first and come back later. Okay, 3.465 also. Okay, and 3.59. Okay, so I think that's it for now. All right, you can go ahead and put it in the chat, but I just won't be able to see it once I share the screen, unfortunately. So let me go back to sharing the screen where I was, if I can. Okay, so let me see, 3.449 somebody asked for. 3.449, whoops. Okay, 3.449, y equals square root of 1 minus secant of t. Okay, so that's 1 minus secant of t to the 1/2 power. All right, so y prime is, whoops, 1/2, 1 minus secant of t to the negative 1/2. Then by the chain roots times the derivative of the inside. So derivative of 1 minus secant t, well, derivative of 1 is 0. Derivative of negative secant t is negative secant t tangent t. So let's see, how am I going to clean this up before I take the second derivative? Negative 2 is on the bottom. This thing is on the bottom. And I have secant t tangent t on top. Okay, so y double prime, let's see, I don't even like the negative, so let me pretend it's a -1. So the derivative of -1 times the function is -1 times the derivative function. Okay, so here's the minus sign once and for all. Now I'll pretend that the problem is just like that. Ignore the minus sign. Oh, you know what? I might as well take out that 2, -1/2. How's that? Okay. There's a coefficient of -1/2. So now I'll just focus only on that. Secant t tangent t over radical 1 minus secant t. Okay, so denominator times the derivative of the numerator. Derivative of secant t tangent t, that's going to be a product rule. So first times derivative of second, derivative of tangent is secant squared, plus the second function times the derivative of the first function, derivative of secant t tangent t. So what did I do? Bottom times the derivative of the top. Okay, so derivative of the top is first times derivative of the second plus the second times the derivative of first. Yeah. Minus top times the derivative of the bottom. Okay, we just did that. It's not nice. 1/2 1 minus secant of t. This problem just doesn't end. Raised to the -1/2 times the derivative of the inside, which again is negative secant t tangent t. All over the square of the denominator. That's nice. The square of a square root is just that. And I would say just stop there. That's so bad. That's probably all you feel like doing. Okay, 3.465. Okay, I'll show that to you again. And this is being recorded, so if you want to check the video. Okay. 3.465 requires us to look at the text. Okay, so they have U, V, and W. So U is f of g of x. So they want u prime of 1. So u prime of x is f prime of g of x times g prime of x. Now for part A, they want u prime of 1, so I plug in 1. U prime of 1 is f prime of g of 1 times g prime of 1. All right, so first I look at g of 1. G is the blue function. Blue function, x equals 1, y is 3. So this thing is 3. G of 1 is right up here. Blue function right there. So I want f prime of g, f prime of 3, g prime of 1. Okay, and the primes means slopes. Okay, so I want the slopes of these. So f prime of 3, 1, 2, 3, I'm over here. Okay, so I have to figure out this slope. It looks like negative. Okay, so the best way to find a slope there is to find two convenient points. Here are two convenient points. It looks like it's over 1, 2, 3, 4, and down 1. 1, 2, 3, 4 to the right and down 1. So that slope looks like it's negative a quarter. G prime of 1, all right? So blue graph, slope at 1, right here. It's also negative. Looks like it's over 1 and down 1, 2, 3. So that's a negative 3. So that comes out to be 3/4. So the answer to 65A is 3/4. Okay, the others are similar. How about I'll show you CW is g of x. So it's a function composed with itself. So w prime of x by the chain rule is g prime of g of x times g prime of x. It just so happens that these are the same function, but that's allowed. Okay, and they want w prime of 1. So w prime of 1, I just plug in 1. G prime of g of 1 times g prime of 1. Right, so g function, blue function. Pretend the red function is not even there. So first I want g of 1. G of 1 is 3 again. This is 3. So I need g prime of 3, g prime of 1. Okay. Slope at 3, slope at 1, only for the g graph. Okay. So the g graph, so what's the slope at 3? 1, 2, 3. Okay. So it's over here. So find two convenient points right there. That's over 1, 2, 3, up 2. So this looks like it's 2/3. Slope is 2/3. And the slope at 1, we already did that, right? That came out to be negative 3, over 1 and down 3. So it looks like it's negative 2. All right, so that's as much as I was going to do for that one. Somebody asked for 3.5, number 9. Let's see if I can do that one. Yeah, 3.5, number 9. 3.59 x squared over x plus y equals y squared plus 1. For this one, I'm going to make it easier on myself by getting rid of the fractions. Okay? Now you might say, do I have to do that? No, you don't have to do it, but you'll be making life much easier. Okay? Otherwise, you have to do a quotient rule, right? Quotient rule is probably one of our least favorite rules. Okay? So I will decide to do this first. That way I don't have to do the quotient rule. I am going to have to do several product rules, but that doesn't bother me as much. So these guys just cancel out. So x squared plus, okay, so just follow that out. Oops, equals. X squared equals, sorry. Okay, x, y squared. First, outer, y cubed. And, well, 1 times x plus y is just x plus y. Okay. All right, now I differentiate implicitly. Okay, the derivative of the left side equals the derivative of the right side. Okay. If you take a derivative and x is involved, it's just a regular derivative as before. But if you take the derivative and there's a y involved, if you differentiate with respect to x, you have to tack on a dy dx. Okay, so this one is 2x. Nothing more, because all you have is x. This is a product rule. First function, second function. So first times the derivative of the second. So the derivative of y squared, 2y, and since there's a y, dy dx. Plus second function, just copy the second function. Don't take the derivative of the second function, just copy the second function. Times the derivative of the first. But what's the derivative of x? 1, so you don't really have to write it. I'll put it just for completeness, times 1. But in the next step, I'll just leave it off. Okay, what's the derivative of y cubed? 3y squared times dy dx. Plus the derivative of x, 1. Plus the derivative of y, 1 times dy dx. Okay, and now all the dy dx's are on one side. Everything that does not have a dy dx comes on the left side. Okay. You say, can I move all the dy dx's to this side? Yes, but then they'll all be negatives. I'm trying to avoid as many negatives as possible. They're already all positive. So I'm going to leave the dy dx on the right-hand side and move to the left side anything that has no dy dx, which is y squared and 1. So these two are going to jump all the way over here. So it looks like I have 2x minus y squared minus 1. Okay, so that one moves over, that one moves over. So on the right-hand side are all the dy dx's, which are this one, and this one. Since they all have dy dx, I'll just factor it out. Dy dx parentheses. Okay, so this is 2xy, and then plus 3y squared, and plus 1. So dy dx, 2xy, dy dx times 3y squared, dy dx times 1. Okay, now you just divide by that and you're done. Okay, so I'll sneak that over here. Dy dx is this thing. And you're dividing both sides by that. So 2xy plus 3y squared plus 1, like so. And that can be your final answer. All right. Okay, that's that. Let's see. Y to y squared for 3.5 number 9. Yeah, we talked about that already. Let's go back to Sharing the screen again. Okay, so right here, product rule. Okay, so first function x times the derivative of y squared. Okay, so what's the derivative of y squared? 2y dy dx. Plus second function. Don't take the derivative of the second function, just copy the second function, y squared. Times the derivative of first. So I'm not differentiating the y squared. It stays, I'm differentiating x. What's the derivative of x? Just 1. I don't need an extra dy dx. So just leave the 1 there. Okay. All right, so that's that. I have a few minutes left. Since I have a few minutes left, let me go ahead and try to complete the logarithmic differentiation that I started. It'll just save some time for tomorrow. Okay. So I introduced the logarithmic differentiation here. So back to here. Right, so I've already talked about this, so getting back to this. The derivative of the left side is 1 over y dy dx. This one, you don't need any d extra whatever because it's all extra. So the left side again is 1 over y dy dx. Right side is going to be 1/2. What's the derivative of that? 1 over x minus 1. Minus the derivative of that is 1 over x to the 4th plus 1. But then it's times the derivative of this, which is 4x cubed. Okay, so here's all that again. So this will be 1 over y dy dx. Then I have 1/2. The derivative of ln x minus 1 is 1 over x minus 1. And then by the chain rule times the derivative of x minus 1, but that's just 1. Okay. And then minus derivative of this is 1 over x to the 4th plus 1, 1 over x to the 4th plus 1, times the derivative of x to the 4th plus 1, which is 4x cubed. Okay, so essentially what you have now is 1 over y dy dx times all this stuff. The last step is always just to multiply both sides by y. Okay, so I multiply both sides by y, that cancels out. But you don't leave your answer as y. What was the original y? The original y was this. So don't write it as y, write square root of x minus 1 over x to the 4th plus 1. So here's the best final answer. 1/2 is there. Y, here's y, radical x minus 1 over x to the 4th plus 1. And then I just clean this up. 1 over x minus 1 minus 4x cubed over x to the 4th plus 1. Okay, so let me run through the logarithmic differentiation process again. Right? So if you're doing logarithmic differentiation, take ln of both sides. Do some algebra here. That's ln of blah, blah, blah to the half. Half gets to come down. I have ln of a quotient, which means ln of the top minus ln of the bottom. Now I do logarithmic differentiation. This is always just going to be 1 over y dy dx. That never changes. It's going to be 1 over y dy dx. Okay. This one that I was starting to show you, 1 over y dy dx. Okay. So 1 over y dy dx equals the derivative of the right-hand side. So we differentiate the right-hand side. You get all this junk here. And then the last step, to isolate the dy dx, you multiply both sides by y. So this cancels out. But you don't leave your answer as y. You write what it originally was. Okay, so there's the 1/2. Okay, so here's the y. Y was all this stuff. So copy that. And then this new factor, which is 1 over x minus 1 minus 4x cubed over x to the 4th plus 1. Okay, so I'll come back to this tomorrow. But for 43, again, that was variable to a variable, x to the x. I'll show it to you tomorrow. You start off by taking natural log of both sides. Once you ln both sides, the x gets to come in front, and then you get the process rolling. Okay, so this side's always going to be the same. It's always going to be 1 over y dy dx. Okay, but we're out of time today, so I'll finish this tomorrow. Okay, So that's about it for today, folks. So tomorrow I'll do logarithmic differentiation, and then after a certain amount of time, I'll stop and give you the quiz for tomorrow. All right. Okay, so that'll do it for today, folks. So have a good afternoon, and we'll see you all tomorrow. All right. Bye, everyone. Bye.